Can you see now what I am sharing? Class?
Yes, sir.
Yes, sir.
Okay, good. So we will start. Our lesson for this afternoon is about stress concentration, which is caused by a sudden change in form. Okay, so stress concentration is caused by a sudden change in form. Okay, if you refer to figure 2-12, okay, it says here 2-12, start here, consider the example of figure 2-12. Near each end of the bar, the internal forces is uniformly distributed. Okay? So meaning on this end and also on this end, they are uniformly distributed. And that is represented by the equal spacing of the arrows. Okay? Uniformly distributed. Okay, so you will notice that the arrows are equally spaced on the left end and on the right end. Now, however, when you reach the portion in the middle where there is B, you will notice that there is a crowding. There is a crowding near the surface of the arrows. And it is not the same space as on the middle. So in other words, at B, on the surface of B, there is a crowding or a concentration of the internal forces. While at the middle between the surfaces, there is an even distribution. So that is what is known as stress concentration, which means that the stress on the portion of B are higher compared to the one on the middle. Between the surfaces of B and A, if you go to the middle, it is not as crowded as you go to the surface of the bar. Okay? So, the nominal stress is the stress is found by dividing the total small cross-section divided by the internal force. Okay, so ang nominal stress na to is how much is the internal force on the right. You consider the smaller, you consider the smaller part, this part here. Okay, the smaller because the other side is bigger. So the internal forces, by the way, the internal forces on both ends are the same, but their areas are not. So the nominal force, a nominal stress should be based on the smaller area. Okay, so the nominal stress is computed on the smaller area. So that is what it means. Stress concentration is there is a higher stress on the surface of the bar compared to the one at the middle. Okay? Any question? That is illustrated by that, no? Any question? Wala ra? So let's proceed to another section. Okay. This time we have a hole on the bar. Of course, if you look at the left end and on the right end, the stress distribution are even. That is in figure 2-13. Figure 2-13, the bar as a whole. Okay? So the stress distribution on the left end and on the right end are identical. However, if we draw a section, putlo na to na siya kanina hole, if we draw a section, you will notice that there is no material on the hole. So, there should be some of the parts which are still holding will carry the stress. So that is why near the hole, the stress are higher, or still another, we'll consider it as stress concentration near the edges of the hole as found in figure B. So you will notice that this part here is higher compared to the one here, the one on the edges. So near the edge of the hole, the stress concentration as represented by longer arrows is higher compared to the stress on the edges of the bar. Okay, so this, as highlighted, no, this irregularity in the stress distribution is caused by the abrupt change of form is called stress concentration. Okay, so the irregularity of the stress distribution because of the abrupt change of form is called stress concentration. So, what is stress concentration? It is better to define it with a formula. A stress distribution is equal to the highest value of actual stress on the fillet, notch, hole, katong nitaas na stress, katong na stress concentration, the value of that stress divided by the nominal stress given by the elementary equation of the minimum cross-section. So atong minimum cross-section dire sa for figure 12 to 13 is the force divided by the area except the hole. No? So except the hole, walay labot ang hole pag kuanin mo sa area. That is your nominal cross-section. So, nominal stress na siya, no? So, the nominal cross-section is kanang walay labot ang hole. So, the nominal stress is the internal force divided by a smaller cross-section. So, we expect a nominal stress to be force over area, where the area is the one that is holding the stress. There is a PICAS, sa PICAS na figure, ang atong nominal stress is of course internal force divided by the area of, by this area. We do not consider this one, no? We do not consider this area, the big area. The smaller area, that is for figure 2-12. So the nominal stress is the internal force divided by the smaller area. Okay, so that is the meaning of stress concentration. As soon as there is an abrupt change, no? Abrupt change of cross-section, you would expect on the surfaces to have stress concentration. Meaning, the stress there is higher compared to the stress on the other part of the cross-section. Now, stress concentration factors K is defined as the highest value of actual stress on that fillet, notch, or hole, meaning katong nainitaas na value sa stress over the nominal stress. Okay? So, stress concentration factors. You will have tables there are actually tables that you can see. No, you have table 2-14. It is for a flat bar with a load of tensile load. Napailain na rin, no? That's 15. It is for a cylindrical shaft with abrupt cross-section. The load is tensile. For 2-16, it is again for a flat bar, but this time the load is a moment load. And there are still more other, no, these figures, no, figure 2-17 and other more, no, depending. So for this 2-17, it is a shaft with abrupt change of diameter where the load is moment or bending. Okay. So any question regarding the explanation of what is stress concentration? Any question? Wala na. There are more figures there, no? Available. This is, you can find this in the PDF file that I have given you. Okay, wala na question, so I'll go to okay, let's go to the to here. You have an example here. Can you see the board now? Can you see me now?
Yes, sir.
Okay. So
Yes,
what we
sir.
have here is a flat bar. The bigger width is 2.25 inch and the smaller width is 1.25 inch. This is your fillet radius, which is 1/4 inch. Now, we are going to find the stress concentration factor, no? This is the stress concentration factor K when the bar is loaded in tension, when this is loaded in tension. So, if you look at the figures, what are the appropriate figure for a bar where the load is tension? What figure? Okay, 2-14, a flat bar with tensile load. Okay, so you use 2-14. And then you will notice in the figure, you need the ratio of the fillet radius over the small d, fillet radius over the small d, and you also need the big D over the small d ratio. So you take that ratio, this will be 0.2, and this will be 1.8. From that, let's go back to the figure. Can you see the figure 2-14? Class?
Yes, sir. Sir.
Okay. So 2-14. According to our computation, R over D is 0.2. So it is somewhere here, 0.2. No? R over D is, the small letter R over small letter D is 0.2. 0.2, no? So nada siya dire, kini. Okay. And then, your D, capital D over small letter d is 1.8. So you will notice that the smallest capital D over small letter d is 1.01, then you go to 1.02, 1.05, 1.1. Okay, so 1.8. So this is 1.5. This is 1.5. 1.5. You divide that into 5, probably you will have 1.8, no? So approximately it is somewhere here. Do you follow?
Yes, sir.
0.2, approximately it is somewhere here. Yeah, napita. So, based on the K value, I have approximated it to be almost 1.8. Okay, naman siya din nakita. No? I approximate it to be 1.8, almost 1.8. So my approximation is 1.78. 1.78. That is for our K stress concentration. Do you follow how to get the stress concentration factor K? The one on the left. The one on the left is your stress concentration factor K. Any question? Do you follow? Okay. So I'll go back. So do you follow how we get this? Class? Since it's
Yes, sir.
approximation, probably you'll have 1.8 or 1.79, 1.77. Huh? If you follow, it's just about the upper limit should be about 1.8. No? You divide it by 5 karang duha ka dato ng 1 point isa ning sa taas 1 2 yeah 1.5. You approximately divide it by 5. So okay, tagkuan man na siya. 1.5, 1.6, 1.7, 1.8, 1.9, 2. So you approximately divide it by 5, then you can approximately get that value. And that is also true for letter B. Okay? The same for letter B, our R over D and D over D, since we are using the same bar, will still be the same, 0.2 and 1.8. 0.2 and 1.8. But the graph is different. What graph are we going to use? So, do you follow, class? Class, do you follow?
Yes, sir.
Yes, sir.
Okay, so we will go to flat bar with bending moment. So it is figure 2-16. Again, 0.2 ang atong R over D. Point 2, and then capital D over small letter d is 1.8, so it is here. Okay. Sorry. 1.8. So 1.2 man is siya, and this is 2. So you approximate it here. It is closer to 2 than 1.2, so probably it is somewhere here. So it's around close to 1.5. Remember the graph or the line or the plot of the curve is between d over d 1.2 to d over d 2. Can you see that? 1.8 man atong kuan. It is between this. 1.8 is between this. So it is somewhere here. So it is close to 1.5, but not 1.5, no? Do you follow?
Yes, sir.
Yes, sir.
Okay. So I approximate it to be 1.48, almost 1.5. 1.48. Okay na? That is how to use these figures, no? To determine the stress concentration factor K. And there are many other figures. If your material is a shaft, no, or a flat bar, and depending on the kind of loading, whether it is tensile or moment, bending moment. Okay? So I'll go back. So we will have the same value of d over d 1.8, and then the same value of r over small letter d 0.2, and we approximate our k to be 1.48. Okay, now you might ask, since the stress in that surface portion, no, it's only a part of the material where there is an actual or abrupt change of cross-section, but it is only on the surface, as you have seen it on the figure, on the letter B, no? Because that is where the stress concentration occurs, no? Atong mga line nga gahuot, ga-concentrate sila. Pero if you move, no, katong lines nga gahuot, concentrate sila. Pero if you move towards the center, they will be spaced equally. So ang stress concentration is only on the surface, near the surface of where the abrupt change, as indicated by letter B. Diyan na siya sa surface. Now the question is, can this affect the strength? No, can this affect the strength? Okay. Now, for ductile materials, if the load is steady, we don't neglect the effect of stress concentration. Okay? We don't include the effect of stress concentration. In other words, we neglect. Okay? The effect of stress concentration are neglected with ductile materials. Why? Because ductile materials have the ability to be deformed. So, at higher stress, ma-deform sila. But they will not, unlike brittle. If you have a brittle material, if there is a higher stress, mukrak na siya. Dili siya, it will not retain its shape. So pag crack ana niya, diretso na siya kabuak. So that is why for ductile materials and steady load, we neglect stress concentration. However, this topic is important because later on in our discussions, we cannot neglect any more stress concentrations. Okay? Okay na ta, class? You have any question? Those who are online? So, muna siya ang na. Stress concentration is that portion where there is an abrupt ha, pero gradual ra, then probably you do not have any stress concentration because your stress distribution will evenly space out, no? Pero og mukalit ra og change, maghuot tong sa kilid. Pero og hinay gani, hinay ra po sila kuan. So meaning they will be evenly distributed. So this occurs at abrupt change of cross-section. Now, endurance limit. Next topic is endurance limit. Now, the key word here is that it is subjected to continuously varying stress. That is now not steady. When you say varying, when we say varying, meaning it is not steady. Okay, for example, I am pulling this, let us say, I am pulling this material, and then the load is pulling this material, and the tensile load is, let us say, 500 pounds. However, it did not change. It is always 500 pounds, so it's steady. However, if, for example, you vary the load in a considerable short period of time, so probably half second it is 500, and in half second it is 200, half second it is 500, or probably you can also opposite it, not tensile compressed. That is now a varying load. No? So that is the meaning of a varying load. Now, the behavior now of materials with varying load is different. We have what is known as the endurance limit. Okay? So, many machine parts are subjected to continuously varying stress. When the stress is below a certain value called the fatigue or endurance limit, the part will last. Okay, the part will last indefinitely. So there is a stress value, if a little bit smaller than the yield point, that if you continue applying the varying stress, no, if you continue applying the, if you continue applying the varying stress, if the stress is small enough, then your material will not fail. However, if it reaches at a certain stress, no, the forces acting will cause it to reach a certain stress value of fatigue or endurance limit, then your material will fail. Okay? So, for slightly higher values, failure can be expected after a certain repetition of the stress cycle. And then, fractures will occur. Fractures, mangliki siya, no? Just like a brittle material. So, fractures, kanang bukog na ma-fracture, mabuak man na, di ba? Oh. Those who are familiar with kanang mga piang-piang. So, fracture is, mo-break siya. Okay, so, fractures will occur without perceptible stretching resembles the failure of a brittle material. Even if your material is ductile, but it is applied with a varying or fluctuating load, when it fails, it will fail like a brittle material. Mudritso rin sa kabuak, dili na siya muinat. No, that is the one. So, fracture occurs without perceptible stretching. Remember, a ductile material is supposed to stretch. But even if this is a ductile material, if the load is fluctuating, then it resembles the failure of a brittle material. So what is the endurance limit stress? Okay, it is sigma E. Defined as the maximum value of completely reversed bending stress with plain specimen such that it can sustain 10 million or more load cycles. Okay, so once you reach that, you apply 10 million. If it does not fail, you have not yet reached. No, ani ko dere makita ko. You apply a fluctuating load. No, bira kuani mo, and then you reach 10 million, it did not fail, so wala pa ka naabot sa endurance. You increase until such time na pag-abot sa 10 million, it already fails, then that you have reached the endurance limit. Okay, and how is this done? How is this done? Lisod man kayo nga magsige ka ganana, no? Now, the setup here is you have a shaft. The load is, of course, simply supported shaft. There are bearings here, and the load is on the middle. You try to rotate the shaft. What will happen to the element? Oh, remember, more circle. Let's remember again, more circle. Oh, remember more circle. In the more circle, the element will show the stresses. Now, what happens if your element is on top? Kaya gatuyok man siya. So, at one time, it is on top. At another time, it is in the mid and the elevation level. And then at one time, it is below. So, what happens when it is on top? What kind of stresses will it experience? Of course, this is bending, no? What kind of stress? Okay, what kind of, remember, in the bending stress, there are two, diba? The MC over I. We cut the cross-section of they are not the same. No? They are not the same if you cut the cross-section. If you have a material, and then there is a moment, what will happen there is that you will have something like this. It is not the same. On one side, it is different on the other side. That is the bending moment. What is the stress here?
Compressive.
Compressive on the top and tensile below. So your element will, if your element is on top, it will experience compressive stress. If it is below, your element will have a tensile stress. Okay? Do you follow?
Yes, sir.
Do you follow?
Yes, sir.
Okay. So that is what will the element experience when you rotate the shaft. As you rotate the shaft, it will have a maximum, remember, MC over I. Your C is the radius when it is on top. However, this is your shaft. Your C here will be the radius. However, when it is your element is here, that is your C. When your element is here, that is your C. When your element is here, that is your C. Distance from the neutral surface to the part where you are want to determine the stress. So basically, from here, it experiences maximum tensile load and gradually reduce. Mugamay siya. What happens when it reaches the neutral axis? Your stress will be zero. Then, once it goes up, it will reverse. It will reverse, it's gradually increasing. And then also decrease until it becomes zero on the neutral surface. Okay, do you follow, class?
Yes, sir.
Okay, so that is what will the element on this rotating shaft will experience. Okay, so if we try to plot the graph, it is a completely reversing. Pareha siya o value sa imong when it is on top and when it is at the bottom. Now, when you reach a certain value called the endurance limit, when you apply this stress, no, padakan mo ng load, of course, you will have your bigger M, the same C and the same I, and then you let it rotate for 10 million. If it does not fail, then you add some more until such time that it will fail. Then you have reached the endurance limit. Okay, so this is your endurance stress. Reversing, no? Now, the value of the endurance limit is dependent on the condition of the surface of the specimen. Polished surfaces have higher endurance limit than rough surface specimens. You can see that in figure 2-11. Okay? There is a figure 2-11 there. Can you see what I'm sharing, class? Can you see what I'm sharing?
Yes, sir.
Okay, let's look at 2-11. Saan naman to? 2-11. Dapat sa taas. Okay. Here. This is figure 2-11. Can you see what I'm sharing?
Yes, sir.
Okay, the graphs there represents how to get the endurance limit of a certain material with a surface of, the first graph is as forged. The second graph is hot rolled. The third graph is machined, and the fourth graph is ground. Okay? Now, this is tensile strength is another word for ultimate strength. Tensile strength is another word for ultimate strength. Okay. Now, what do you mean by as forged condition? The surface of the material is as forged. Do you have any idea what is as forged or forged condition? Okay. It is the surface where the material or the specialist steel comes out of the factory. So, meaning it has a very rough surface. No, remember, rough na yung surface, ana. So, if you produce steel, usually you melt it and then pour it to a mold. So, unsay surface, ana, mana siya as forged. Now, the next part there is to shape it, katong imong mold nga material, shape it into a certain shape where you let it pass through a roller para they will be of equal thickness. So this time, what surface will you experience? A little bit smoother than as forged. How about machine? Okay, you use any machine. You can use shaper, milling machine, lathe. Okay, all of those wherein there is a tool bit or a bit that is cutting to the surface, and you would expect a much smoother surface than a roller. Okay, and of course, what is ground? What do you mean when you say ground? Okay, unsa may mo pasinaw? Okay, sanding is one of the ways of grinding. But of course, grinder. A grinder is a way of grounding. But you can still make it smoother with a sanding. No? So that is the ground condition is the smoothest surface of the material. And you will notice that your endurance, the one on top has higher endurance compared to the one at the bottom. No? Kaya ang imong endurance limit is on the left side. Okay, do you follow the graph? Do you understand the graph? Do you understand what the graph represents? Class? Class, can I hear
Yes, sir.
feedback? Okay, so, okay na tana. So let's go back. So again, the value of the endurance limit is dependent on the surface of the specimen. So polished surfaces have a higher endurance limit than rough surface specimen, as we have found it on figure 2-11. Okay, we will have an example. Any questions so far? Let's proceed with an example. Wala?
Wala, sir.
Okay. Let us look at this example. What we have here is, by the way, this is still a continuation, no? For ductile materials with completely reversing stress, you will find out that initially, with steady, if you can remember, steady, factor of safety for steady is yield point over the actual stress. Yield point over the actual stress. This is for steady, for ductile materials, steady and ductile materials. However, when it is now a reversing load or fluctuating load, instead of yield point, we now use the endurance limit, and we put the stress concentration factor. Okay? So we now include the stress concentration factor. So for steady ductile materials, we can neglect the stress concentration factor. However, if it is, even if it is ductile material, as long as it is reversing or fluctuating, by the way, the difference between reversing, completely reversing, is that once it reverses, it has the same magnitude. Okay? How much is this tensile? That will be also the same compressive, completely reversing. However, in certain cases, in fluctuating, dili parehas og value. In fact, in some instances, it will not go to compressive or tensile, but it is fluctuating. So something like this. So all is tensile. O pwede po nga puro compressive tanan. These are fluctuating loads. And pwede po nga na tensile o na compressive. Bas dako ang tensile sa compressive. Something like that. But as of the moment, what we're discussing is a completely reversing stress or load. Okay. So, now, unsa man ang range stress? It is actually the stress. Remember, when you are the stress that is from the average, remember, on the middle is the average stress, to the outermost stresses, no? And I said, that is your range stress. Because, for example, in that case, our average is 0. No? Remember, when it is completely reversing, before it reverses, it has a value of 0. Then it reverses completely the same magnitude and go back to 0, and then opposite direction, the same magnitude. Okay. However, in certain cases, nadiri atong kuan, probably ana siya. So, this is your average. That is your average, and your range is this one. So, that is the meaning of range. Range stress is the swing from the average. No, ang iyang kuan, labay dito og dire. This is your average. Because later on we will be discussing stresses wherein the average is not 0. But for completely reversing loads, then our average is 0. So that is the meaning of this range stress. Okay, example. We have a freight, a class E. We have a class E freight car axle, and it carries a load of 52,500. The material is a medium carbon forged steel. It's a barrel hardness number of 180, and the ultimate strength is 90,000 psi. Ultimate ni siya, and the material has a forged condition. So, we are going to find the factor of safety. So, first, since it is an axle, where do you find an axle? Okay, it is on the wheels. Wheel and axle are always come in pair, no? Wheel and axle. So this is your wheel, these are your wheels, and this is your axle. Now, who has an idea what is a Class A freight car? Okay, it is actually, this one is, it is like what you say, similar to what you see in the sugarcane, no? Sugarcane kanang who runs on rails. Udagan sa mga rails, no? It is like a train. It is like a train. So the wheels here are steel. The wheels are steel. And of course, your axle are, according to the material, is medium carbon forged steel. Now, the brittle hardness number, of course, what is given is the ultimate strength. Okay, so what we need, so as this, we are going to find the factor of safety at the center. You will notice this is a little bit tapered, but it is not abrupt change of cross-section. So, in this case, we do not have to consider the stress concentration factor. Although it is not of the same, it is not of the same. If you look at this in the PDF file, it is not the same diameter on the sides and on the middle. Okay. So what we need here, since it is rotating, then if you examine the element, it will be moving around in circles. Then the stress that it will experience is Reversing. Ano siya? Completely reversing. So, what we need is, of course, the endurance limit. Endurance limit. And later on, we will compute for the range stress. Okay. Now, how do we get the endurance limit? What is given is the ultimate. So, asa man ta mangita ana? From where? Remember, if you know what is the ultimate or the tensile strength, it is given, and then the endurance limit is not given, unsa man to tong gikuan kaniya? Unsa man to? What figure?
211, sir.
2-11. Okay, figure 2-11. If you look at 2-11, tensile strength is ultimate strength, no? Tensile strength is ultimate strength. And our ultimate strength, according to the problem, is 90,000 psi. So it is somewhere here. Between 80 and 100. Do you get? Do you get the? So, what is the surface? Condition of the surface? As forged. So it is here. So our endurance limit is approximately almost 20,000. 20,000 psi. No, almost. So I approximated it to be around 19,500 psi. Huh? Nine sa kwan. Tensile strength 1,000 psi. Nasa ubos. So it is 80,000, 60,000. The tensile strength 60,000, 80,000, 100,000. Okay, do you follow? Do you follow? So it is close to 20. I approximate it to be around 19,500. No, very close, almost 20,000. Do you follow, class?
Yes,
Yes,
sir.
sir.
Okay na ta. So, I go back to the problem. So, my endurance limit for this material, which is as forged, the axle is as forged, then its endurance limit is 19,500. Now, how do we determine the range stress? Oh, lagi, it's completely reversing. So, kinanglan man na dire. We cannot determine the factor of safety. Okay, what is the use for the moment? Okay, first, let us look at the load. Do we know where is the load? Only the weight of the axle. What is the load? Class.
52,500, sir.
Okay, according to that problem, it is 52,500 pounds. It carries a load of 52,500 pounds. But the question here is, that 52,500 pounds is on the car, not on the axle. It is only the axle that carries that 52,500. Now the next question is, where does it act on the axle? Because dili po na siya pwedeng maglutaw-lutaw ra niya, yung axle mudagan ra po siya iya. It has to act on the axle, the 52,500 pounds. And which part of the axle is it acting? Here? Okay, if you're 52,000, let us say this is your car. This is your car. Okay? I'm going to draw it. These are your wheels, and this is your axle, and you say that this is your 52,500. Is that correct? So meaning, your 52,500 is acting on the middle of the axle. So probably your car is here, and it has to balance. Kinahanglan, mayong pagka-balance ang imong kuan. Do you have a car nga nasa tunga sa axle ang kuan?
Uniform daw doon nasa.
Huh? Do you have a car wherein auto name mo ba? Ana imong, let us say this is your car. Front, sorry. Muna yung mga wheels niya. Front ko ang lahat ng ganon. Axle na siya. Naa ba kay car nga, naa-diri sa tunga ang kontak? Nya kini siya mo balance ag maayo. Ha? Naragod siya diri magkuan. This is your, remember, ana na siya, ana na car ha. Front view ni siya. Front view. Now, it is acting on the middle. Meaning, your car has to balance properly. Dili siya pwedeng matumba diri, di pwedeng matumba because it's only acting on one location.
Dua, sir, sa kilid.
Okay, so it should be here. We are looking at where the 52,500 is being passed. The load of 52,500 is being passed to the axle. So, ug mas nato nga, may pagka-balance ang kuan. Ayaw kuan na kay matumba ta. No? Ayaw gimo ka kay mananin pagka-balanse. Kuan na nato isa ka tubo dere matumba na ni, madugangan na tong isa ka tubo. If it is. Okay. So it is in contact with two locations on the axle. The question here is at what part of the axle?
Tapad sa ligid, sir. Dua.
Okay, tapad sa ligid. So, dire?
Oo, sir.
Dire napita. Now, with Class A freight car axle, it is different. The wheels are inside. So which means naa siya direga kuan contact. Meaning Kita ba mo, if you have seen a freight car, na siya iligid diha, you will notice nga natabunan na siya, dili makita. Because dili ka kakita og kanang iyang kuan, because the wheels is inside. The wheels is inside. So if you are going to look at it, this is your freight car, that is your axle. It is actually here. And then your wheels are here. That is why you cannot see the wheels in the kanang most of the trains nga inyo makitaan, no? Gawas there are also some trains nga makita gyud nimo ang wheels sa gawas. No? But for this it is inside. So, in other words, which part of the axle is the 52,500 in contact? Okay. The one with the X. Okay. So it is concentrated here and here. So it does not have to be balanced, no? Bisan pag dako dire gyapon siya matumba. Sa to nga kinahanglan may siyang pagka-balance. Okay, so the forces here and the forces here, the total is 52,500. Now, since it is proceeding along a smooth straight level, meaning level ni siya, then your stress distribution from to here is symmetrical, meaning what? Meaning what? How much is the force here and also the force here from the load of 52,500? Equal, which is how much? 26,250 acting here. And the reaction on the wheels will be where? Okay, from the wheels reacting that way. So since it's also identical or symmetrical, then our reactions here are the same, to 26,200. Okay, so now let's go to what stress will the car axle experience? Atong range stress na atong kanon. How do we compute that? Remember, it is your element is from top to bottom, no, going around in circles. So what are the stress that is being involved and how do we compute that stress? When you have a load like this, no, what causes it to, what are the causes? By the way, we are going to compute it on the middle, no, according to this. Factor of safety at the center of the shaft. What kind of stress do we expect? And how do we compute it? Moment Or another term for moment is okay, ang may tabuan ni is kana siya mag-ana man na. Kani po siya mag-ana. So naa dere and this one is 26,250. Pounds, and this is also 26,250 pounds. And of course, this one will also be 26,250 pounds. So what kind of stress will we experience in the middle? Ngano na compressive man? So remember, gadut anay na sila dire. So the tendency is to mana siya. Kani po sa pikas, mana siya. So your axle will tend to be shaped like that. When you have a flexure or a bending, what kind of stress is it? Okay, bending or flexural stress. Now, your bending or your flexural stress is, of course, in that direction, no? Kaya ana man. Ana man po ni siya. So, it will shape like that. So, when your element is on top, what kind of normal stress does it experience? Ana yung bawog. Tensile. The one on the bottom, compressive. Okay. So, what we need now, what's the formula how to compute the flexure or the bending stress? MC over I. Okay. I is of course the cross-section area moment of inertia of the cross-section, which is circular. It is pi d to the 4th over 64. That is for I. Now for M, how do we determine the moment here? You can draw the shear and moment diagram, or if you want a shortcut, you just cut this here and find the moment on the left or on the right. No? Pwede po ka drawing of shear and moment diagram until you shear and then you get the moment, no? Okay, magkuhan ka na, muna yung load. Dayo na kay kuhan na anak man eh. Ayun ni sa ubos. Ayun anak, no? I think anak na po. Something like that. And then you take the moment. However, for a shortcut, you just cut the section of the axle and then find the moment either on the left or on the right. Okay, so I cut it here. What is the moment on the left? Pila? Pila? 26,000 times 9.5. Dari ni mo gikuha ang moment? Hindi rin man ta magkuha ang moment. Remember, dito magkuhag moment. So what are the moments of this? About here. Any idea? I'll take moment here. So what should be? Moment is what? Oh, see, unsa may force? 26 to 50. So you are taking moment here. Abi na kog dire. Asa man ita mag-MC over I? Dire di ay. Unsa man? Any idea? Magkuhatag moment dire. Di na mo kabalo kuhag moment?
Times 29 and 3 over 4, sir.
Times 29 and 3 over 4. So your force is here.
Plus 9.5.
Plus 9 and a half.
9.5.
Okay, so that is for this one. So it is 29 over 3 over 4 plus 9 and a half. That is your moment on that side. Then, wala na. Isa ra ka buok? There's only one, only this one?
Napa, sir.
Unsa pan?
Kanang R, sir.
Sir,
Oh, R. What is the direction of R compared to this one?
Opposite, sir.
So it should be what?
Negative.
Minus, sir.
negative, sir.
Times
29 and 3/4, sir.
Okay, you compute this. You try to compute that.
$249,375, sir.
249,000
375.
inch pounds. Okay? Now you will notice in my calculations it is only 26,250 times 9 and a half. And you will get the same answer. Why is that? Because these two forces are equal and forms a couple. And do you know what is the moment of a couple? Oh, you know what is the moment of a couple? The moment of a couple is, so bisag asa nini mo sila ibutang dire, you will have the same moment. That's the moment of a couple. Meaning this is 26,250 and that is also 26,250. And the moment for that of a couple is force times distance between the two couples. Which is 26,250 times their distance. But of course, this is how it is supposed to be if you do not know what is a couple. But since I know what is a couple, that the moment of a couple is equal, taken anywhere. Ang moment ani niya, bisag asa ni mo kuhaon, is still be the same. So, there ni mo kaon, ang moment niya is still 26,250 times its distance between the two. 9.5. Oh. Muna akong gamit diri. This is the moment of a couple nga 26,250. No? Opposing the moment of couple which are opposing forces in opposite direction but are spaced in between. There's a space in between. Then the moment of that, you take it anywhere. Isag-asa na nimo mo kuan. Mo guna mo gawas. Force of 1 times the distance between the two. You try that. Dire ko no kuha. Because you will find it here, no? What will happen? You distribute. What will happen here is negative 29 o yakini positive. Makancel ni sila. Unsa may magawas? Kini na lang 9.5 times this one. Class, do you get that, class?
Yes, sir.
Yes, sir.
You try to simplify this because this is a moment of a couple. So 26,250 times 29 plus 26,250 times 9.5. Yan na po kay negative 2650, 29. So these two will cancel and what you will get is 26,250 times 9.5. But what is important there is that a couple, two forces in opposite directions but are spaced, no? Wa sila gatagbo, but they are spaced apart. Their movement, even if you take it anywhere, will be the same. So the force times its distance. So I'm just leaving it here. This is how you do it, no? Because in certain cases probably dili na ni parehas og forces, dili na siya couple. Okay, you now have moment. Your C now is what? Okay, what is that? Dili, what is that? Kanang katunga ana. On the shaft, what is that? It is the radius of the shaft on the middle of the part, no? There is a tunga, center of the axle. Because the radius here is a little bit bigger. So on the center, the radius is 1/2 of 6 and 7/16. Okay, so that is our MC over I. And then our range stress is now 9,000. This is the maximum stress, huh? Remember, when your element goes on top, unsa man yung bawog ani ana? Ana di ay. Sorry ana. No kay giduot man ana, mana na siya. Giduot na pud dire mo balik. So, ana ang atong bawog. On top is what? Na imong element dire on top what? It is that, but what kind of normal stress? Okay, you will have a tensile stress on top equal to this one. If you move downwards, tutuyok na imong shaft, ana ra po yung bawog, what will be the stress below? And it will still be this one. It still be that one. So of course, your factor of safety is the endurance limit over the range stress. Our range stress is 1 because there is no abrupt change of cross section. Wala man di specify diri nga nikalit ra sa gamay. In fact, gradual ang iyang. So, meaning the stress distribution is even all throughout. So, your ratio of the katong maximum stress and nominal stress are equal. So, your K is 1. So, your factor of safety is 2.048016. Any more questions?
Sir, question, sir.
Yes,
Kanang
go ahead.
ultimate stress, sir, ug kanang range stress. Unsay pinagkalahian na, sir, ug kanang maximum stress?
Unsa to?
Kanang range stress, sir, ug kanang ultimate stress.
Wala man tayo ultimate dere.
So range stress, sir, tong ano?
Range
Naano
stress
din
is the maximum stress that is being experienced by the material.
Okay, sir.
So we compute that by the formula because it is flexure or bending by the formula MC over I. Do you follow? The range stress, since it is flexure or bending, then we compute it by MC over I, where C, of course, is the radius that will give us the biggest stress, which is on the surface of the shaft, which is the radius. And then that is the range stress. So meaning, as your element goes from top to bottom, it will experience a flexure or bending stress of this much. On top, it is tensile. Below, it is compressive. Okay, ana yung bawog. So when your element is on top, it is tensile. When it goes below, because this is rotating, it is compressive. That is range stress. Do you follow?
Yes, sir.
Do you follow?
Follow to, sir.
Unsa to? Unsa pa to imong ultimate?
Wala ra, sir.
Endurance is property of the material. How much it can carry a reversing load. That is for the endurance or the fatigue stress. So, naana sa imong material. Ang range stress is actually the stress that is being experienced because of the load. Ang imong endurance, ato nang pangitaon sa figure. Given the ultimate or the tensile strength. Unsa pay lain?
Sir, dili ra maka-affect ng force sa pika side sa pagkuha sa moment, sir?
You take moments. You cut the section here, you take moments on the side. Do you follow?
Yes, sir.
Now, when you cut your section here, you just see one side. If you look at it on the other side, parehas na gyapon. You do the same.
Magkalahi ng load ana, sir, sa left and right nga ano, sir. So lahi pud ng
Really, it will be the same. It will close because it will close. Even if the numbers are not the same. Because your moment diagram will close. So the amount of moment on one side should be equal to the amount of moment on the other side. Any other questions? Wala na question? Unsa man? What do you mean? Sa flat bar dayon, unsa given? Depende sa imong kuan. Ug unsa imong design. Oh, it is given that okay, depende man nimo. For example, na kay kuan gi-design yun ana iyang mga dimension, di mo na siya imong kuan. Mga dimensions na siya sa kuan sa imong unsa imong gi-design. And then you can also vary. For example, pag check nimo, pag compute nimo mo kuan, you try to evaluate o padak-an nimo na siya unsay mahitabo o pagamyan nimo na siya unsay mahitabo ana. Any more questions? Class, any more questions? Those who are joining online, wala na? You can take pictures of the notes, those who are here in the in person. Do not touch the camera, no? Okay, mag-screenshot mo. Class, you take your screenshot. Are you done with your screenshot? Let's go to the other board.
Yes, sir.
Okay.
Excuse me, sir.
Yes.
Naani i-clarify sa factor of safety, sir. Kining 9,521.41, ang sigma R na sa isa ang range stress. So, ang K may 1 ano sa isa.
You're talking about this one?
Kanang under ana, sir.
Okay.
Diba
Now,
ang K may 1.
as I have mentioned, since there is no mention of abrupt change of cross-section, then our stress concentration factor is equal to 1. But I have placed it here because that is the formula. But it is supposed to be, pwede niya butang agwan. Yeah.
Okay, thank you, sir.
Remember, when there is no stress concentration, then the stress concentration factor is equal to 1. Because as defined, stress concentration factor is a ratio of the highest stress to the nominal stress. Since the nominal stress and the highest stress are equal, because there is no change or abrupt change of cross-section, then your K is 1. Are you done with the screenshot? Class, are you done with the screenshot?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay, so I'm going to ask you to turn on your cameras. I'll let you first erase the board, no? Before niya na. Okay, kuan pa. Dili, kuan na. In fact, i-arrange unta og kuan nga kanang mga kuan kabuok dagway. Lima kabuok in each row. Yeah, mga tulo ka rows. 5. Arrange og 5. I-space og mayo. Kuan pa. Relay pa mga diri dagway lang kuan di ana. Kuan, tulo dagway ka, tulo ka kuan. Tulo ra kasi ikuan irog dagway diri jutay. Ana. Dugangig kuan dito. Okay, turn on your cameras please. Turn on your cameras. Okay, class, since wala na may question? Wala na?
Wala na, sir.
Okay, so thank you for this afternoon's successful online and in-person lecture.